No,
I can't unmute. Oh, I can.
yeah, yeah.
No, I can't. This is like very We are live. Good evening, one and all. So today we are having a live session for gas dynamics, fundamentals and applications. So all of you are welcome to ask any questions on the course so far, anything you have not understood or you need more clarifications. We will try to provide you with that. So today I have with me, so I am the instructor Srisha Rao, a professor in Indian Institute of Science, and with me I have Lakhan and Shrikar, the two teaching assistants for this course. You can type your questions on the chat over here and we'll be able to read it and answer. Not able to get it? So for the exam, you will be provided with gas tables. So you can use the gas tables that is provided to you in the exam. Who is asking the question?
Okay. Question from Samuel. So, can you please explain about strong shock angle increasing with increasing Mach number for constant theta?
Okay, so I hope you are talking about the M theta beta relationship, or is it a shock interaction relationship? I think it's only strong shock angle. For every particular Mach number and given flow deflection angle is theta, you have two solutions for the shock angle. One is a weak shock solution and the other is a strong shock solution. In the weak shock solution of the oblique shock, the flow downstream of the shock will generally be supersonic. So, and in the strong shock solution, it will be subsonic. The angle of the strong shock is larger than the angle of the weak shock. The strong shock will be approaching close to the normal shock. Okay, so they have much larger angles. Okay, so if you look at the behavior of the m theta beta curve as you change Mach number, so there is a point. There are 2 points actually important in the m theta beta curve. One is the maximum shock angle, that is for an attached shock. So you have a wedge and then the flow is going over the wedge. Then there is a maximum wedge angle for which the shock is attached to that to the tip of the wedge. And beyond that, you don't have an attached solution. The shock will become detached. So that's the maximum shock angle. You have one more point, which is the sonic point. Okay, the sonic point is the point where the downstream Mach number is unity for a given upstream Mach number. Usually these two points, the sonic point and the maximum flow angle point, both are very close to each other. So the curve actually goes from a minimum of the Mach angle at zero, that is almost you don't have any flow deflection. As you keep increasing flow deflection, the weak shock solution goes from Mach angle to the maximum shock angle. Okay, and then again the strong shock solution for zero deflection is nothing but the normal shock, and then as the angle you give higher and higher, the angle slightly reduces. Now this maximum shock angle, if you see as you keep increasing the Mach number, okay, so this maximum shock angle keeps increasing. Okay, so that is the behavior of these curves. Okay, so you will have two solutions for any given shock angle. So if you draw a constant theta line and you take it up, you have many curves of different Mach angles, different Mach numbers. Then you will see that for a given theta, as Mach number increases, the angle will come, the weak shock angle will come closer and closer to the shock, I mean to the body. That is how the behavior of the shock is. Okay. I hope I have answered your question. Yeah.
Okay. How entropy changes across the shock wave? Okay. What is entropy and how it changes across the shock wave? Can you explain in detail, please?
So entropy is a thermodynamic quantity. So it relates to several things which we discussed very early on in the thermodynamics as applied for gas dynamics. So it comes in the second law of its definition comes in the second law of thermodynamics. In general, it is thought about as the state of disorder in a system, order or disorder. More entropy means more disorder. It also has relationships to availability, how much work can be done, available energy, unavailability, and so on. And generally, increase in entropy will lead to decrease in efficiency. A lot of things related to entropy will be discussed in the core thermodynamics classes. So it is best to sort of go through in detail in that at that point. Here we take that we know what is entropy and what happens to entropy across shock waves. Entropy increases across shock wave because shock wave is something which is irreversible. It generates a lot of irreversibilities. So within we really what we do in analyzing shock waves is we consider that shock waves are discontinuous and they're extremely thin, so this assumption is valid. And we don't go and resolve what is happening within the shock, but really within the shock, all the viscous forces, thermal conductivity, all these kind of things dominate, and they cause a lot of entropy increase. So all the viscous forces that we had usually neglected in the implicit considerations, because of the very large gradient that is there across the shock, they will become very important within the shock. But shock structure itself is not solved for because it is extremely thin, and in the continuum approximation that we do, it can be considered as a discontinuity. And we apply jump conditions across the shock. So we are only solving for variables across the shock, not what happens within the shock. The net effect of all these things is that entropy increases across the shock, and it is a cause of irreversibilities, and therefore the net entropy increases. You can say that presence of large, strong shocks is not good for the efficiency of a system. If you want a very efficient system, then you should keep shocks. If shocks are inevitable in supersonic flows, there are many systems like diffusers or intakes which work in supersonic flows. They use shock compression, but they are effectively designed in such a way that they minimize this entropy production by using relatively weaker shocks rather than very strong shocks. I hope I have addressed that question.
Yeah, yes, sir.
So a question from Mohit Kotekar. Question is, why does the stagnation pressure show absurd behavior across a shock, whereas the stagnation enthalpy and stagnation temperature remains the same?
Okay, so stagnation pressure reduces. There is nothing absurd about it. Okay, so that is a direct consequence of the increase in entropy. So you can shock is extremely thin. So when we do the analysis of shocks and we draw a control volume around it, there is no scope for any heat exchange and so on. So it's an adiabatic system. Therefore, in an adiabatic system, and there is also no addition of any heat or any work being done. So then if you look at the energy equation, the basic energy conservation equation, there is no heat transfer, there is no work done. Therefore, the total energy, total enthalpy, H plus V square by 2 has to remain constant in such a system. Okay, but there is entropy production in the system. So now what is the effect of this entropy production? If we take a look at that, you can see that for every state in a flow, you can always define a stagnation state by looking at an hypothetical isentropic process. So you can get the stagnation pressure and stagnation temperature at every point. So if you look at it before and after the shock, by the consequence of the conservation of energy principles, stagnation temperature cannot change. But entropy change across the shock can also be related to changes in the stagnation conditions of the shock. Stagnation temperature remains same, but stagnation pressure changes, and stagnation pressure decreases due to an increase in entropy. Always stagnation pressure will reduce, and it reduces rapidly with increase in Mach number of the shock. I hope that's you have got the clarification.
Hello, sir. For a choke nozzle, P is not equal to PB, but in case of CD nozzle operating and design condition, we assume P equals to PB. Even the flow is choked and supersonic. Why is it so?
Okay, so yes, that particular condition, that when the exit pressure of the let it be any choke nozzle or let it be any conversion diversion nozzle producing a supersonic flow, there is only one particular point for a given stagnation pressure or reservoir condition, as we say, uh, at which the exit pressure of the nozzle will be exactly equal to the ambient pressure or the back pressure, as the case is. That particular point is called the design point or the operating point. So many names people call it, usually called the design point. Okay, so when you are at the design point, then the nozzle operates perfectly. It will expand completely and give the pressure at the exit exactly equal to the back pressure or ambient pressure, because you designed the nozzle for such a pressure condition. If for any reason, either the reservoir condition changes or the ambient pressure or the back pressure changes, then the nozzle will work in off design condition. So all the other cases, whatever we refer to as under expanded or over expanded conditions, they're all off design conditions. There is only one design condition where following a perfect expansion, the exit pressure of the nozzle is exactly equal to the back pressure. This the distinctions come only after the point that the nozzle chokes. Okay, before the nozzle chokes, the flow is subsonic. The boundary condition for a subsonic flow is that always the exit pressure of the nozzle should be equal to the back pressure. These differences of back pressure and exit pressure arise because once the flow becomes sonic at throat or at the exit, whichever as the case may be, then there is a breakdown of communication or information propagation from the downstream of the nozzle to upstream. So upstream communication gets blocked because of the property of these supersonic flows themselves. Therefore, the flow is no longer able to know what is the pressure downstream. So it will expand or continue to expand according to the geometry that is given, but at a later point, you'll find out that it doesn't match the pressure. And in order to match pressures, it will, as a consequence, start producing shock waves or expansion waves, as the case may be. So when you are considering convergent divergent nozzles or nozzles which are choked, convergent nozzles which are choked, you cannot always expect that the exit pressure will be equal to back pressure. There is only one point where it will be equal, that is under perfect expansion conditions at which the nozzle is designed. Okay, is this clear? If there is any further query to this, to ask.
So always it is not possible to achieve design condition, right?
Yes, it's not always possible to achieve design conditions. A very simple example is of a rocket nozzle. You can think about the rocket nozzles, the flow from the rocket nozzles as they go from lower atmospheres to the lower atmosphere to upper reaches of the atmosphere. We know the pressure of the atmosphere, it keeps decreasing as you go higher and higher. The nozzle will be designed for some particular condition, say particular altitude. So when you are near the sea level, the nozzle has an ambient pressure which is much higher than what it is designed for. Okay, but as you go higher and higher beyond that particular altitude at which it was designed for perfect operation, the ambient pressure will reduce. So this nozzle, it is fixed, it doesn't change, right? The nozzle for the rocket nozzle has a fixed geometry, and for given fixed geometry there is a definite relationship between area ratio and Mach number. Once you provide enough supply pressure, enough stagnation pressure so that the nozzle chokes and it's able to produce the supersonic flow, then you will always get, initially you will get, if the pressure is, ambient pressure is higher, it will be over expanded, then it will become perfectly expanded, then it will become under expanded. So uh, because these nozzles, in general, these nozzles, you cannot change geometry in between. Of course, you can design, make it a design feature that you have a variable, a nozzle whose area can be varied. It can be made as a design feature, but otherwise, most of them are fixed. Once nozzle geometry is fixed, its relationship to Mach number and pressures is fixed. Therefore, at the exit, you can always have either under expanded or over expanded conditions you can get, and only under specific conditions the nozzle will operate under perfectly expanded conditions. So yes, the variable area duct can undergo off design conditions.
Okay, why there is a mass motion induced behind the moving shaft?
Firstly, shock waves are not like other linear waves like sound waves and so on, which produce only infinitesimal change in pressure, density, and so on. The change produced by shock wave is very large. Okay, so it is not at all in comparison to such waves. And by its very feature, when the shock moves through a medium, uh, it not only it imparts higher pressure and temperature, but it will also pull the gas along with it. It induces a mass motion with it. Okay, so that's from conservation of mass, momentum, and energy, you can show, just because the shock wave has so much of energy and it is trying to dissipate that energy, it will induce this mass motion. So in a shock tube, what you would find is that the production of a shock will induce a mass motion along with the shock, moving from, if I say the driver section is on the left hand side and the driven section is on the right hand, then the shock moves into the driven section. Behind it, there is a gas motion or mass motion, which also moves along with the shock towards the right hand side. But in order to conserve mass and momentum and energy, you will get an expansion wave system that will move towards the left. So it is the nature of these moving shocks that they produce these induced mass motion.
So a question by Samuel. So question is, for an overexpanded CD nozzle, is there a possibility of formation of a normal shock at its exit?
Yeah, so for a CD nozzle, what we say is, yes, there is a particular condition, which is the second critical point. This is under quasi 1D analysis. Under quasi 1D analysis, you get the point at which the flow is completely supersonic within the nozzle, but you can have a normal shock at its exit, and thereafter the flow is subsonic. That point is called, so the first critical point is when the CD nozzle is choked, and it's first choked, but the flow is subsonic throughout the nozzle, before and after the throat. The second important point, second critical point, is this particular point where you have complete supersonic flow within the divergent portion of the nozzle, but right at the exit you have a normal shock. That is an important point you can consider in the operation of CD nozzles. But if you see really pictures of CD nozzles, there you would observe more that these shocks are what you call as normal shocks, are more having a little more structure. They have more like a sort of Y or lambda kind of structure, because near the nozzle exit, you can have boundary layers, and those boundary layers can affect the shock, and shock will affect the boundary layer, and some complex features develop, and they can give rise to these lambda kind of shocks. But even in such shocks, somewhere a large part of the shock, which is lying near the center of the duct, will be normal to the flow. Okay, so yes, under very high pressure conditions. So the for exact operation of the nozzle, you have to provide the correct nozzle pressure ratio. If you don't provide it, rather you provide a higher ambient pressure corresponding to critical, that is corresponding to critical point number 2, you will get the possibility of a very strong normal shock at the exit.
How this changing frame of reference affects flow properties across the shock wave?
Okay. Frame of reference is important when you consider moving shocks. And certain properties across the shock, like the static properties, pressure, temperature, static pressure, static temperature, they do not change when you change the frame of reference, either when you are sitting on the shock or you are looking at it from laboratory or fixed frame of reference. But if you change the frame of reference, then stagnation properties undergo a change as they are based on relative velocity. So since they have relative velocity component in their estimation, the relative velocity will change when you change frame of reference, and therefore your stagnation properties will change. So you can see that by the fact that in a stationary shock, when you do the analysis, the assumption, or no, rather the fact is that the stagnation temperature remains constant. But for a moving shock, you can see that the stagnation temperature increases as the shock passes over a particular point. So yes, so stagnation states change when you change frame of reference, but static states do not change.
Okay. Uh, can you please explain the exact difference between Mach number m star and m critical?
I really not. M star is the star Mach number that you find by dividing the velocity with the critical velocity or speed of sound, critical speed of sound, and critical speed of sound or star speed of sound, as we say, is the speed of sound that is evaluated through an isentropic process from that particular point to a point when velocity is equal to the acoustic speed. Okay. So that's a hypothetical process. You can evaluate T star and then get A star, and B by A star is what we call a star Mach number. Sometimes it is also called as critical Mach number. But critical Mach number has other meanings also in the context of when you talk about going transonic and airfoils and so on, where you have a critical Mach number there. That implies the point where the transonic effects become very dominant. That is, your flow that is oncoming is subsonic, but over the airfoil, the flow can accelerate to supersonic conditions and then create a shock and then cause very large drag and so on. That is those kind of that has a certain association with critical Mach number. So where the Mach number where such effects become very important is known as critical Mach number. So we really have to look at the context. If you're talking about airfoils and you're talking about critical Mach number with respect to that, it is this particular flow phenomena of production of normal shocks for the first time over the airfoil, causing large drag, flow separation, and so on, leading to very high drag. So that is critical Mach number. The star Mach number is related completely different. It is the Mach number is defined as velocity to the star acoustic speed. Okay.
So, a question by Shashank. Question is, the maximum Mach number obtained in a divergent duct is 1. This is true for however large this divergent duct is. Is it right?
The maximum Mach number obtained in a divergent duct. I do not know without knowing the boundary conditions, because as we have discussed in the variable area ducts, you have to really define boundary conditions to really say how a variable area duct will behave. If you take only purely a divergent duct and you're going to give it initially a supersonic flow, then it will just accelerate it to higher velocities. Okay, so what is the boundary condition? That is important. If you give a sonic flow, that is, if you give a sonic flow at the beginning of a divergent duct, then you will get supersonic flows. So anyway, again, your Mach number will increase. But if it is behaving like a diffuser and you have sonic flow entering a divergent duct, then it will lead to a decrease in Mach number. But that is decided by the pressure ratios across it. So that means you have a very weak shock formation at the throat, at the minimum area. So what are you implying? And that has been sort of emphasized in the lectures, that you really have to look at when you say convergent duct or a divergent duct, you have to say whether what are the boundary conditions, whether it is behaving as a nozzle or a diffuser, because the same duct can behave as a nozzle or a diffuser if you change what is the incoming boundary condition. In a supersonic flow, if the incoming flow is supersonic, then the boundary condition will change, the behavior will change. Okay, so I hope I have answered your question, because you really have to specify where. Just by saying it's a divergent duct will not solve the problem. Is it operating in supersonic regime or is it operating in subsonic regime? That part has to be clarified.
So question by Bhargav Desai is explain the exact difference between Mach number, M star and M critical.
Yeah, I think I answered the question.
If you attach diverging section to test section, so can we take it as A2 star for diffuser? If you attach directly divergence section to the test section, so can you take test section area equals to A2 star of the diffuser?
If you attach the diverging portion, so what you would get, you would not get it exactly into star of the, because you would get some, you need to have a shock wave there uh, in order to reduce the flow velocities. So if the divergent duct is behaving like a diffuser, then that means necessarily the flow that is going to enter the divergent portion has to be subsonic. But if you don't have a convergent portion, so it's not a convergent divergent diffuser, then this will always lead to the production of shock waves in the test section. Okay, so you will have to then evaluate. It's not necessary that immediately after the shock wave you consider under a quasi 1D assumption, it will be a subsonic flow. So the area of the test section cannot be considered as A2 star in such a case. The flow is not sonic at that point. If there are no further questions, we can close the live session today. Thank you one and all. Thank you Lakan and Shrikar for helping with the live session.